So thank you very much for the invitation. It's always wonderful to be back in Warsaw. Okay, so here is so this is the title. So it talks about invariant and quasi-invariant measures for actions of oligomorphic groups. So it is also some type of ergodic theory like maths, except that I will deal with much bigger and more complicated groups. I'm here only talking about just actions of a single transformation, which is the action of the group of integers. And here somehow the groups will be very big. But then somehow the bigger the group, I mean, the fewer actions it has in a way. So you can say more things. I mean, you actually do have classification results as opposed to the non-classification results that you get. Okay, so I think I will spend probably most of today talking about this. These oligomorphic groups, so these are types of permutation groups. So I'll define everything and maybe develop some of the theory. There's some connections with model theory and other things. And yeah, also so don't hesitate to interrupt, ask questions. Okay, so maybe I'll start with some definitions. The main objects that we want to discuss. So we start at some countable set. And then we look at the group of all permutations. The group of all permutations. This is a set of projections. From end to end. So this is naturally a topological group, and topology is so this pointwise convergence. Okay. Set M is take to risk. Okay, so if you want a basis at the identity. Stabilizers of finite sets. And so here the whole point in this group and groups like this is that these stabilizers of finite sets, they're subgroups. Okay. So this is it's a special property that the topological group may have, is so having a basis at the identity consisting of open subgroups. Okay, so maybe I'll write this here. So say that the group is non-Archimedean. It is like this. Okay, so the group is if there is a basis identity consisting of open subgroups. Okay, and then it is a simple and well-known fact that these non-Archimedean Polish groups is exactly the same thing as closed subgroups of this infinite permutation. And so there is sort of a small subtlety is the right word, but this non-Archimedean Polish group is an abstract thing. And here, when I look at the subgroup of this thing, it's actually a permutation group, right? Because any subgroup here, it comes already equipped with an action. Okay? And this, the only thing this tells you is that, of course, so closed subgroups, this group, they satisfy this property. And conversely, it is easy once you have something like this, you can actually find a set N and then realize the group as a permutation. Right, and so another, probably the most important definition for the whole thing. It's another property of topological groups. So group G is called relatively compact. It's this funny thing. So if you haven't seen this before, it's maybe a bit strange. If the following thing happens, so for every open neighborhood of the identity, there exists. So this is open. There exists a finite set F. Finite. U. F. So maybe I'll spend 1 or 2 minutes of trying to explain where this comes from, why this code like that. So the first thing is, let's say if you remove one of the U's, so if you just do this, yeah, that so for every open neighborhood there are finitely many translates of it that cover the group. Well, this is the same thing as compactness, right? Well, if you assume it is complete, if you do not assume it is complete, it's the same thing as pre-compactness. You can complete it and get a compact. Okay, so this is. But here we also allow for multiplying by this issue, both on the left and on the right. So it also does correspond to pre-compactness in some uniformity. So it is well, it's called the Riolicke or the lower uniformity of the group. Doesn't matter so much. So there is a completion with respect to this uniformity, which is actually a compact, space, but it is no longer a group. So this is why I mean this thing is not maybe so well known as compact groups, but still I mean these groups they have many nice properties, and well, most importantly I mean there are a lot of examples of sort of big groups that satisfy this. So sort of a typical example is this, for example, this symmetric group that satisfies this. Okay, I mean I'll give like a long list of examples. Okay, so for non-Archimedean groups, I mean this definition it actually well somehow becomes simpler, but there is something slightly more you can say. So if G is non-Archimedean, so this is equivalent. So for G non-Archimedean, this is equivalent to the following thing: that for every open subgroup, open subgroup of G, it has finitely many double cosets. Okay, so this. So what is right? What are these double cosets? I mean, I'm sure you know what the single cosets are. These. So double cosets are the same except that it's on both sides. So it's just orbits, right? So what is a double coset? It is just an orbit of the action of V times V on G, right? I mean, it's just an arbitrary subgroup, and then V times V it acts on G by left and right multiplication. So the left copy acts by left multiplication, and the right copy acts by right multiplication. Of course, on the group, left and right multiplication commute. So you get an action of this. And a double coset is just an orbit of this action. So that's all. And then, well, just so here we just have times.
You have for all V something G.
This set is finite.
No, one sequence for all V less than or equal to G sub what?
So for every this is open, sorry.
Open, okay.
Yes. So for every open subgroup, there are only finitely many double cosets.
Okay.
So, okay, maybe I'll say a little bit more about this when I explain the model theoretic part. Okay, and now so what is the connection between this and permutation groups? So there is also, sort of, if you want, the corresponding permutation group property that corresponds to this. So this is this oligomorphic business. So let's give another definition. So now this is a property of a permutation group. So now G is a subgroup of Cn. And so we say that G is oligomorphic if for every k, the diagonal action G and k has only finitely many groups. some sense, it tells you, yes, that G is big inside here. Of course, for the full group, this is true, right? I mean, for K, you have, well, have to count somehow how many orbits there are. It's not so simple because things can be equal and so on. But there is some clearly a finite number, and then this tells you that, well, that if the group G, it has sort of few orbits, this means it is somehow it's a big group inside here. Okay, and then so one more definition, which is, okay, so G is called locally oligomorphic. If so the restriction of the action of G to finitely many every equals any finitely many orbits n so what does this mean? Right, so in particular, if you want oligomorphic, in particular for k equal to 1, there are finitely many orbits. So the original action only has finitely many orbits. And so here you relax this restriction. So maybe the original action, it has infinitely many orbits on it. But then once you restrict the action to any finitely many orbits, so basically if you assume the condition for k equal to 1, then you automatically get it for propositions. Okay, so this is just a definition. Okay, and then so what is the connection between those two things? As you can imagine, I mean they're the same. Which okay, so I'll write the precise statement. So for let's see, how do I want to write it? One, if G is a subgroup and with finitely many orbits. So if you assume that the orbits are finitely many, so then the following are equivalent. So is one is that G is locally compact as a topological group, and two is that the action is oligomorphic. So if we assume that the group only has finitely many orbits, then the two things are just the same. So this is a property of the group, and this is a property of the action. And two is without this assumption. We just have this. And then what is equivalent is the same, but you have to replace one. So again, G is locally compact. Two is that the action is locally occurring. So this local condition is it's a little bit annoying. I mean, it would be much nicer if you can just deal with oligomorphic groups, which also have somehow a nicer model theoretic interpretation. The problem is that somehow the natural generality from a topological perspective is this serial precompactness business. And then, okay, maybe non-Archimedean because, well, otherwise it is harder to say things. But you cannot, so the thing is that it is not true that you can realize every permutation group faithfully, make it act on a set with only finitely many orbits, right? I mean, imagine, for example, if you have a compact group, imagine you have a profinite group, which is infinite. And then there's just no way you can realize it faithfully. I mean, on action with only finitely many orbits, right? Because we need infinitely many orbits just to see how, I mean, to see the whole group. So this is why this this thing comes up. So this is basically the thing which I'm going to use. I mean, basically put these locally oligomorphic actions all the time. But if you think about this situation here, I mean, if you sort of know what this is, you're not going to lose much. And somehow the correct generality to the things is here, but somehow a lot of the examples here, and then the intuition. So maybe now is the time to say something about the connections with model theory. So, if you want examples of things like this. So if now M is the structure, so if M is the count of a structure, so model theory structure, with relations and functions, so on. Then, well, this is theorem of Université. So the following are equivalent. So the M is Aleph-zero categorical. This is a slight abuse of language. So the theory of M. Okay. This means that the first order theory of M has a unique countable model of isomorphism. 1 and 2 is that the automorphism group there's a permutation group acting on M is oligomorphic. So this also is, if you want, is the main sort of examples by this theorem. It is the only source of examples. But somehow it allows you to a lot of things. So maybe just I don't know. So if you haven't seen these things before, I mean, this will just give you a few examples to think about. So what is the easiest way to produce Aleph-zero categorical structures is by looking at homogeneous structures or Paris elements. Okay, so we'll maybe say what this is. So M is homogeneous if for every two finitely generated substructures, so A, B, finitely generated substructures of M, and every isomorphism from A to B extends isomorphism. And so, well, things like this is so they're produced using set theory. And it's a way to produce structures like this. And then this oligomorphicity business, so having only finitely many orbits up to isomorphism just tells you that at the end there are only finitely many n-generated structures up to isomorphism. So that's all. So this is very easy to achieve. For example, if your signature is relational and it has only finitely many symbols. And of course, automatically, well, n-generated structures, they have n elements, and well, because there are finitely many symbols, they're only finite. Okay, so this is there's some of the main examples. So examples, for example, structures, so homogeneous structures. Typical example. So this is the full symmetrical. So this corresponds somehow to the empty language. So there's nothing except equality. Or always give the same examples, and this is somehow I think it's a little bit unfortunate. So this is the automorphism group of the rational linear order. So this is also a very well-known one. Yeah, this is homogeneous structure in the order, or maybe the random graph. Or there are any more examples. And I sort of assume that people have seen things like this before, so I don't want to spend too much time on listing examples of race elements, homogeneous structures, and so on. So I think by now it's probably seen this many times. But what I was saying, so I think that the unfortunate part of this is that we only give somehow examples of this type, which are very simple. I mean, and then somehow actually the world of Falley zero categorical structures, it is much richer, and like many more complicated things can happen if you allow infinite languages and then imaginary elements and so on. And somehow a lot of what I'm going to say is that it will be very easy to see, for example, like this, but it's less easy to see generality. The actual generality of these oligomorphic. I mean, there's actually a lot of structure which I think is not has not been fully explored. Yeah. Explored. Right, but if you've never seen things like this before, I mean, these are maybe examples to keep in mind. And then I mean, I'll probably give more. Have to go. Okay. So what else? Okay, so now maybe I'll say a few things about yes.
If I may. So if you don't know anything, it's not Q, it's just Q. It's just Q. That's not Q.
What do you mean just Q?
The structure.
You have two examples of groups, one example of the structures.
Yeah,
that's okay.
Actually, another point to make, if you don't know the things, then yeah, all closed subgroups of sim M are those kinds of things. That's
all what?
Closed subgroups of non-Archimedean groups are automorphism group of structures.
It is true, but then this is an additional property, I think.
Yeah, but
sure.
If you don't know structures, that's a.
Well, I sort of hope that. So I mean, it's a logic conflict. No. Anyway, so yeah, don't hesitate to interrupt and ask. Some things are okay. So maybe I'll say a few things now about what. So think about measure preserving actions. So sort of switch. This is just wrong. This will just introduce the objects that I'm interested in. So now I'll say a few things about measure preserving actions. So okay, so we have the following situation. So we have X, so B. So this is standard graph space with the probability measure. So then an action is so an action of G X is measure preserving. Here, yeah, every when you move inside by an element of G, it has the same measure. On this action, yeah, the action is always supposed to. Okay, and then so you can take, so this is a Boolean algebra, right? The Borel sets. So you can quotient this by the ideal of null sets. So this is known as the measure algebra. Now this is a complete Boolean algebra, and of course, because of this measure preserving condition, the action descends. So if you have an action here, you get an action of the algebra. And it's sort of an interesting question. If conversely you have an action on the measure algebra, whether it is actually, I mean, this is an abstract object, right? This is a complete Boolean algebra. It can be actually continuous logic or something like this. If you have an action like this, does it actually come from an honest measure preserving action on a set? So this is, I mean, it's an interesting question that has been actually investigated quite a bit. I was planning to say a few things, but time is running, so I'll just say it orally without writing things down. So for countable groups, it is sort of trivial that if you have an action like this, then it has a point realization. For non-Archimedean groups, so for the groups that I'm going to consider, this is also true, although it is less trivial, so it is a theorem of Glassner invites. And for some groups, this is not true. So for a typical example is if you just take the automorphism group of the measure algebra, right? Just automorphism group, measure algebra together with the Boolean algebra operations. So this group, it's quite easy to see that the action, the tautological action of this on the measure algebra actually cannot be realized on a pointer. Maybe it's not so easy to see, but it is true. And then there are also many examples.
For any measure?
What do you mean for any measure?
We have this mu here, so this space depends on mu.
Well, so the question is the following. So you have an action on a measure algebra, which is an abstract object, right? So this is just a Boolean algebra together with a measure. The measure algebra has a measure, right? So the question is, can you realize it? Does it come from a situation like this? So does there exist a point action of the group, a Borel action on a Borel set, such that when you quotient, you get the original action? So what I'm claiming is that if you start with the tautological action of this on the measure algebra, I mean the action that defines it, then this does not have a point realization. Okay, it cannot make it act on a set such that this thing happens. Well, the mu is there, right? I mean what I'm saying is that there does not exist an action on a set, and there does not exist a measure there, such that when you quotient, you get precisely this action. Actually, for this group, you cannot get any action. I mean, don't really.
Could you just read the second, third, and fourth line? Could you just read the second, third, and fourth line?
This
second line from the top.
So this one, yes. So I'm saying that the action is measure preserving if for every set, okay, when you translate it, it has the same measure.
Okay, and the next line?
The next line says that it's a Borel action.
Okay, below that.
Below that, yeah, sorry, maybe I should write more clearly. So this is a definition of the measure algebra. So it's just the quotient of the algebra, the signal algebra of measurable sets by the null, by the ideal.
Okay, got it.
Yeah, sorry, I mean, I should maybe try to write. Okay, so this is, but so what you should take away from this is that for the things that interest me in this whole mini course, so I only look at non-Archimedean groups, and there these two things are really the same. So having a point action on a set and having an action at this level on the measure algebra are just the same. So I'm just not going to consider this problem at all. But it's something to keep in mind that it is. I mean, it's a non-trivial fact, and it's actually for some groups it's just not true. Glassner, Philipson, and Weiss. So they have examples for this and also for the unitary group. I mean, there are. Oh, some for non-Archimedean, it is Glassner and Weiss. So the proof is not difficult. You have to do something. Okay. And then there's also the another thing is ergodicity, which Matt already mentioned. So I'll just remind you. So the action is ergodic. If the action on the measure algebra has no fixed points. So the action measure algebra has no fixed points other than 0 and 1. The 0 and 1 of the algebra, yeah. So this is the empty set and the whole space. Right, so these two are always fixed, and you say that the action is ergodic if there are no other fixed points. And so we're usually interested in ergodic actions for this reason of this ergodic decomposition theorem, which basically tells you that every action in one way or another decomposes as an integral of ergodic. So if you understand ergodic actions, this actually gives us a pretty full understanding. Okay, so another thing I wanted to do is I want to give you sort of a cautionary example. So this example was first noted by Kolmogorov a long time ago. I think for him it was a reason to actually not consider actions big groups, because he considers it as a pathological example. But it's a very simple thing. So we have this is the full symmetric group, and then you just make it act on the n with the. You have to put a measure here, right? So we put the Bernoulli measure, where p is some number between 0 and 1. Right, so a Bernoulli measure on 2 is just 1. So we just give weight p to 1 and 1 minus p to 0. Right, so the Bernoulli measure 0, 1, and then you just take the product. Okay, so it's simplest possible measure preserving actions of groups like this. And now, okay, so let's, for each of these, let's go with mu p. So each of these measures, I mean, all of them are ergodic. So this is easy to see. I'm going to prove this in a second. So all of these are ergodic. Now let's consider this set. So AP, so it depends on p. So this is a set of all sequences x. N. So I'm also going to identify this n with the actual natural numbers. Okay, so just fix some arbitrary bijection between my set n and the natural numbers. And now I'm going to look at all x's such that the density of the ones is equal to p. Okay, so this is the limit. Correctly, so a number of I. And so this is all sequences such that the density of the ones is equal to p. Okay, and then the law of large numbers tells you that for every p, the measure nu p, it concentrates on the set AP. Right? I mean, okay, so the APs are disjoint. So the AP are pairwise disjoint. So until here, I mean, there's nothing unusual. So this is actually a completely general phenomenon. If you have ergodic measures, then they concentrate on disjoint sets. So this is a general fact. So what is slightly more unusual and maybe perturbing, if you're not used to this, is that all of these sets, I mean, the measures are invariant, of course. All of these sets, they are in the same orbit of the action, right? Because so this, I mean, this action actually has very few orbits. It has only countably many orbits, and then all of these concentrate on the orbit which has infinitely many zeros and infinitely many ones. Right? This is a single orbit. As long as you have infinitely many zeros and infinitely many ones, well, you can find a permutation that sends one of them to the other. Okay, so you have these continuum many disjoint sets. Each of them, so you have ergodic measure concentrates on each one, but they are somehow in a single orbit. Listen, I mean, this is a perturbing example if you are used to the, say, the locally compact groups or things like this, where this cannot happen. So it's just something to keep in mind. Yeah. Okay, so this is one thing. Then, so maybe I'll say a couple of words about ergodicity of this action and similar actions, and I'll also introduce the main tool of infinite permutation group theory. So this is a lemma. This is probably again the most important tool in infinite permutation group theory. So it is Neumann's lemma. Probably most people know. Is that so? This is completely abstract thing. So you have G acting on a set N, and then the following are equivalent. One is that all orbits are infinite. Is that for every finite subsets A and B, exists G in G, sense A. Okay. So of course, I mean the interesting direction is 1 to 2. The other one is stupid, and this thing is really used a lot. Also there are many proofs. I mean the original proof is entirely group theoretic with cosets and things. I mean there is a formulations of this. So maybe I'll give you the Hilbert space proof, which is the I'm also going to use a lot of representations in Hilbert spaces afterwards. So maybe this will be sort of an introduction to this. Okay, so what is how do you prove this? So let's see. 1, 2, 2. So the thing is, so every time you have a permutation action like this, you also get an action on Hilbert space, right? You just look at so the square summable functions on N, and well, the action is just by shift. So you just take a function and then shift it by okay. This is an action by unitary transformation. Okay, so now suppose that 1 holds but 2 does not. So then there exists sets A and B such that for OG O translates as A intersect. Okay, so what does this mean? Now, it implies in particular that for every G, right, we take, so T of A is the characteristic function of A, so it just gives 1 to the elements of A and 0 everywhere else for the same. So what does this tell you? It tells you that, well, so the G times A and B they intersect. So here, what is the inner product between two characteristic functions is just the size of the intersection. Right. Okay, so this is just this function. So this is because they intersect in non-trivially at 1 point, so it's this one. Okay, so this is the first observation. And then so the second thing that we do is we look at set. So we look at all translates of chi of A, and then we take the closed convex Hilberts. Okay, so it is some convex set in a Hilbert space. And now comes the main point. So this is an important property of geometry of Hilbert spaces, is that every closed convex set has a unique point of minimal node. Okay, so I'm going to write this down. So every closed set in a Hilbert space has a unique element of minimum node. So in particular, because here this set, this set is clearly G invariant, right? Because I just took the orbit of a point. So it's a G invariant set, so the closed convex hull is it's a G invariant set. And by this uniqueness, this point is fixed. Okay. So I just produced a fixed point for my action of G on the Hilbert space. Okay. So this is very nice, except that in most situations this point is 0. Right? Of course you can do this for any action at all, but then very often what you get is 0, which is not so interesting because 0 is always fixed. But here we have a condition which actually ensures that this thing is not 0, right? Because this is a convex condition. So if I take the closed convex hull, it's satisfied all the points. Okay, so I think well, we're practically done, right? So there exists psi 0, and which is fixed. It's not in L2, it is in this closed convex. It's here. And this thing is fixed by G, and so most importantly, non-zero. Its inner product with B is at least one. Okay, but now what does it mean for a point to be fixed? I mean, remember what the action is. So the action is just the shift. So a point is fixed. Well, it has to take constant value on every orbit, right? I mean, this is the same. Well, okay, so it is non-zero. So you know, I mean, if the orbit was infinite and it takes a constant value on the whole orbit, this is no good, yeah, because the function is supposed to be in L2. Yeah, so it has to be square summable, so it cannot take the same value infinitely many times, and it has to converge to zero. So the only possibility that remains is that like the places where it takes non-zero value is actually a finite orbit. Okay, so this contradicts. So there exists a n such as psi 0 a 0, and then the orbit must be finite. But it's a nice proof, and it illustrates sort of a lot of proofs that will probably appear later. Actually, so how long do I have? I have until the hour. This is how it works. Okay, so questions? Okay, so let's prove like another simple thing just for warm up. So it's again it's in abstract setting, so we have so again G on M, and then we have the action of G 2 to the M. Again with this Bernoulli measure, so Bernoulli P this is our favorite action, and then the following are equivalent. One is that this action is ergodic. Is that all orbits are infinite. So so again, so there is one direction which is silly. So I'm not going now. So if you have a finite orbit, the interesting direction is from. So if you have a finite orbit, like what you can just say is that on this finite orbit you're equal to 1. Maybe I should say that P is now. Yeah. I just look at the set which on this finite orbit I'm equal to 1. So this has probability, I don't know, P to the size of the orbit, so which is a non-zero number, and this set is clearly invariant. So this gives me an invariant set, so it's not a. So the interesting direction is the opposite, is that if the orbits are infinite, then actually the action is so it's an easy way if you want to produce ergodic actions, just from this. But actually this is quite, it's an easy application of the lemma from before. So let's see. So suppose that we have some set Z, which is a subset of N. which is invariant. And of course, of measure, so maybe I'll call this measure mu. Measure of z is different from 0. Okay. So now from basic measure theory, you know that every measurable set can be approximated by a set which only depends on finite line coordinates. So let's say that z0 depends only on a finite set of coordinates. Let's call it A. So it only depends on the values of, if you want, these random variables, only on the set A. Does not depend on the others. And it is very close to our set. But now you see, now, well, by Neumann's lemma, we can find a G. Which sends this finite set coordinates to, well, a set which is disjoint from it. Right? This was the whole point. Well, and now what happens is that the z0 is independent from this, from its translate, right? Because so z0 it only depends on the set A. Now I moved my set A to a disjoint set. Well, so z0 depends on A, gz0 only depends on g times A, and these, these coordinates are independent. I mean, this is a product measure. So I got two independent events, so z0 and g times z0, which on the other hand, both of them are very close to z. And it just cannot happen, right? Because, I mean, z is invariant, so it have that z is equal to z. On the one hand, z0 is very close to z, and this one is independent from this, so you basically get that, by taking limits, you get that z is independent from itself. And the only way a set can be independent from itself is it has measure 0. So that's it. Right. So this in particular shows that, I mean, this action which I considered at the beginning was ergodic. It's a very easy way to produce ergodic actions starting from permutations. Okay, so what? Okay, so now I think I'll go back to my oligomorphic things and try to develop a little bit of structure theory about these oligomorphic groups, which I'm going to use later. So, are there any questions? Maybe I'll say just a couple of words but there are not that many model theorists in the audience, at least not that I know, for Todor. Maybe okay, so the connections between these things and I mean, so there's a very, very close connection. Okay, so so there is an equivalence of categories between right, so here is something which is correct. So Ryoke precompact non-Archimedean groups. With morphisms, except that it's not all morphisms, so this is morphisms. Precompacting. So I don't want to time on this. So okay. This is one of the categories. So we have these groups with continuous morphisms with some restriction on the image. Okay, so it's not all morphisms. So this is on one side, and the other one is what is it? is Aleph zero categorical structures. With interpretations. Okay, so this is only to know a little bit. Model theory is well, Aleph zero categorical structure, I think is clear. So interpretations is a way that you can interpret one theory or one structure in another using first order forms. And the whole point is that these interpretations, so they use a lot of equivalence relations. I mean, this is how somehow you interpret the universe of your new structure by taking some definable setting in the old one and quotienting by a definable equivalence relation. And sort of so you get all of the interesting examples actually by having interesting equivalence relations. And okay, this is one of the reasons why a lot of the theorems that I'm going to discuss, we will just exclude this. I mean, we'll basically consider situations which there are no interesting equivalence relations, so that you can actually get stronger theorems. And otherwise, it's less clear. It's less clear what happens. But so this is also an abstract reason why model theoretic tools, they're actually very, very useful in all of this business. So in the end, I made the choice to not use any model theory at all. So I think I'll do everything using permutation groups. But on the other hand, I think I'll probably use a little bit of model theoretic terminology. But then if you happen to know model theory, then the two things should coincide. And the reason they coincide and somehow the correspondence is really so nice is, if you want, philosophically because of this. Because you have two categories which are equivalent, so basically you can translate everything from one to the other in a nice way. Okay, so this was just sort of a philosophical aside. Okay.
So this equivalence is algorithm theta?
Yeah, yes, maybe I should have said this. Okay. Thanks. Right. Okay. So now, let me say one more thing, and then this will be for today. So somehow the abstract setting that I'm interested in, right? So G is Ryoke precompact and non-Archimedean. But I want to use permutation group. So I mean, here there's no action. So the thing is that there's a canonical action of this group, which somehow captures the whole information about the group, which can be constructed as follows. So there's this universal action. Okay. So we just take so U is the collection of so let's see, left cosets. Maybe. Let's call it S. So S is a transversal equivalence relations. Conjugacy. Open subgroups. So I look at all open subgroups of G. Okay, there's very important. I forgot to mention this. So these Ryoke precompact groups, they only have countably many open subgroups. Okay, so this is quite easy to see, but maybe to mention because it's very important. So if you have, why is this? You have, of course, it's a Polish group, so you have a countable basis. And now the whole point is that so if you have an arbitrary open subgroup, there is some element of the basis, which is inside. But remember that this group, it has only finitely many double cosets. And of course, an open subgroup which contains this one, well, it must consist, of a whole number of cosets. So they're only finitely many. Yeah. So this tells you that for every group, I mean, there are actually only finitely many groups above it. Okay, so this is it's a very fundamental thing. So again, for every open subgroup, there exist only finitely many groups which are bigger than it. right? Because of, well, sorry, countably, because if you have, I mean, these finite many cossets, you can. Is it true? No. I got confused. There are only finite many groups. Just because there are finite many double cossets in G, and you just have to take a collection of them, and that's it. Okay. So another thing is that you cannot have a chain, right? You cannot have a chain of increasing open subgroups. This is also something that cannot happen. Again, because of this finiteness condition, right? Because it consists of a whole number of cossets, and then well, there are 10 of them. Okay, so we can have no more than 10 groups. So in particular, the total number of open subgroups is countable, right? Because for each one of the element of the basis, well, there are only finite many that contain it, and they're countable. It's a countable basis. Okay, so now we look at all of them. So this is a countable set. And well, some of them are conjugate. Okay, so there is this conjugacy relation. So some of them are conjugate, and I just take a transversal. So I just for each conjugacy class of groups, I just take one. Okay, and now I take U to be all left cossets of elements of S. So for each of these groups, I take all of its left cossets. And now I just have G act on this. Okay, so I just produced an actual unaccountable set. So it's easy to see that so this action is faithful in the sense that, of course, I get the morphism from G to the symmetry group of U, and then I get G inside as a closed subgroup. I mean, this is obvious. So this is so the canonical part of this is that I took all of the open subgroups. Well, modulo this thing which I'm going to explain, taking only one of each conjugacy class. But somehow, so I produced, so starting with a group, I just produced this universal action, and then, well, the rest of the time I'm just going to work with this. So if you want, again, so if you have a more modulo-theoretic inclination, so this is the same as starting with some arbitrary model. I mean, you take some structure M, you're interested in its automorphism group, and then to produce this universal thing, what you take is this so-called MEQ. So this was something which was introduced by Scheller, which is basically taking all possible equivalence relations and looking at all quotients of definable sets by all equivalence relations. And then this is how you get this. But you can just also produce it from the group in this way. And then, okay, so I think I will continue with this next time. Thank you.
I guess there will be more questions later on. So let's thank Todor again.